Okay, so let's start the class. So today we will continue the discussion on Wilson's theorem. We have talked about this last time, but we didn't give a proof. And then we will talk about a new thing called Euler phi function. And then, if we have time, we will talk about RSA critical system. So this is Wilson's theorem. So it says that if you look at m minus 1 factorial modulo m, okay, the same thing, it will be congruent to minus 1 if and only if m is a prime. Okay, so 6 factorial will be congruent to minus 1 modulo 7. Okay, because 7 is a prime. But on the other hand, 7 factorial will not be congruent to minus 1 modulo 8 because 8 is not a prime. Okay, so by checking m minus 1 factorial modulo m, we take a look of what is the value. If it is minus 1, then it means that m must be a prime. If it is not, then m is not a prime. Is that okay? So we would focus on the case m greater than or equal to 2. It is rather meaningless to talk about m is equal to 1. Okay, so yeah, m is equal to 1, then maybe 1 is not a prime. Okay, so in that case, 0 factorial is difficult to talk about the case of 1. So let's ignore 1. Let's assume m is equal to 2, 3, 4, or so and so on. So let's prove this. So to prove this, we are going to divide the case into 2 parts. One is we find out what happens when m is prime. When m is prime, we want to show that it is going to be equal to minus 1. And then the other part, we want to take a look of what happens when m is not a prime. And then when m is not a prime, then we hope that m minus 1 factorial is not equal to minus 1. Is that okay? So this established the if and only if. Okay? Okay. Now, before we prove this, let's do some review. Okay. So let's consider a prime. Okay, let's say p. Let's say p is equal to 7. Okay. Okay. Now, and then we look at all the numbers less than p. Let's look at 1, 2, 3, 4, 5, and 6. Okay? 6. Okay. And then we argue that, okay, so if you still remember, we have defined what is inverse before, or the multiplicative inverse. Multiplicative inverse. Let's say b inverse of a number b. So this is the number such that it has this property, b inverse times b is going to be equal to 1 mod a number p. Okay? And then so as long as this b is co-prime with p, it doesn't have any common factor, the inverse of b exists. Because GCD of b and p is equal to 1 implies that there must be some number multiplying with b will be a multiple of p plus 1. Is that okay? This is my definition of GCD. Okay, and let's take a look at the inverses here. So for 2, for 1, what is the inverse? Okay. Is there any number that multiplies with 1 will have a remainder 1 when divided by 7? So we talk about modulo 7 case. So always divide by 7 and take the remainder. So is there a number that multiplies with 1 will give us a number with remainder 1? 1, right? 1 times 1 is 1, okay? So if you divide by 7, the remainder is 1. So, okay, 1 times 1 is 1. How about 2? 2 times 4 is 8. 8 is a multiple of 7 plus 1. Is that okay? Now, if 2 times 4 is having remainder 1, then 4 times 2 is also having remainder 1. Is that okay? So these two forms a pair. Okay. It's a pair. How about 3? 3 times 5. 3 times 5 is equal to 15. Okay. Is that okay? And how about 6? 6 times 6. Okay. Okay, so So this is the case for p is equal to 7. Let's look at one more case. Okay. So we have some. I want to claim that this kind of inverses, they form pairs, except 1 and except p minus 1. Okay, let's take a look of another case. Let's take a look of p. Let's try another prime. 13. Let's try 13. Is that okay? Okay. So for 13, let's write down all the numbers less than 13. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So 1 is 1. And then 12 is also 12. 12 is easy because 12 is minus 1. Minus 1, the square of it becomes 1. Okay. And how about 2? So you get 13, right? 2 times 7, it will be 13 plus 1, right? 2 times 7. So 2 and 7, they form a pair. And interestingly, you can have at most one number to form a pair with you. So let's say 2 times 7 is equal to 1. Then 2 times any other number cannot be equal to 1. Yeah, because if you have 2 times 7 is equal to 1. And then suppose that it is equal to 2 times some other number b. Okay, some other number. Then you multiply the inverse of 2 on both sides. You will get 7 must be equal to b. Is that okay? Good. So if 2 has an inverse, it is unique. And then 7 will map back to 2. Okay? How about 3? 3 times what? 3 times, you get 3 times what? 13, 26. Oh, 3 times 9. Is it? 3 times 9 is equal to 27. And it is a multiple of 13 plus 1. So 3 and 9 forms a pair. Okay. How about 4? 4. 13, 4 and 10. Is that okay? Is that okay? 5 and 8. Okay. 1, 5 and 8. Then only 6 and 11 left. So 6 must be mapped to 11, right? 6 times 11 is 66. And then, okay, they form a pair. Okay, is that okay? So first of all, we claim that they form pairs, except 1 and minus 1. Okay, they form pairs, always form pairs, except 1 and minus 1. The reason, what is the reason? So if they do not form pair, then it must be the case that you are going to map to itself. Is that okay? So we are asking, how many cases can we find two numbers, or can we find a number such that itself is equal to 1? Mod p. How many cases are there? Then, if you look at this, this implies what? This implies x, you put the 1 over there. You have x minus 1, x plus 1 is equal to 0 mod p. Is that okay? Is that okay? So x minus 1 times x plus 1 is a multiple of p. So p either divides x minus 1 or p either divides x plus 1. These are the two possible cases that we can have because it is a prime. This is going to be a multiple of p, right? So p divides the product of these two numbers. So p either divides x minus 1 or p divides x plus 1. If p divides x minus 1, then it is a case of 1. X is equal to 1 modulo p. If p divides x plus 1, then it is a case of minus 1. P divides x plus 1, so x is equal to minus 1. Is that okay? Okay? Is that okay? So this shows what? This shows that if we consider a prime p, and then list out all the numbers smaller than p, from 1 to p minus 1, then the numbers will form pairs. One is the inverse of the other, except the boundary, except this number and this number. Is that okay? Now, this is all we need to prove the first part of Wilson's theorem. because m is equal to a prime. Let's say m is equal to prime p. Okay, that's what we are going to look at. We are going to look at p minus 1 factorial, right? We want to check out what is the value, what is the remainder when it is divided by p. So p minus 1 factorial is equal to what? 1 times 2 times 3 times 4 times ... up to p minus 2 and then p minus 1. Am I correct? Okay, now, if you take modulo arithmetic, then you know that 2 forms a pair with some other number. 3 forms a pair with some other number. 4 forms a pair with some other number, right? Only 1 does not form a pair. And p minus 1 does not form a pair. All the other numbers, 2 will form a pair, such that when they are multiplied together, they become 1. Another form a pair, it becomes 1. Everything becomes 1, except this 1, there is no pairing, and except this p minus 1, there is no pairing. So this will be equal to p minus 1. Is that okay? So done. So we are talking about mod p arithmetic. So this is what we can show. The first part of Wilson's theorem. Okay? How about the other part? Okay, but one thing that I want to say is that we need to be very careful. If you see x squared is equal to 1 mod p, it looks like there are 2 x that can satisfy this formula, right? But if it is not a prime p, then there can be more. So for instance, so I'm talking about something strange, okay? Suppose that this is not a prime p. Let's say we change it to 8. Let's change it to 8. What will happen? What kind of x such that the square of it will be equal to 1 modulo 8? One, because 1 squared is equal to 1. Am I correct? We also have 3. 3 squared is equal to 9. We also have 5. 5 squared is equal to 25. And we also have 7. Is that okay? So when we are looking at modular arithmetic, we need to be very careful. Okay, something that is, you think it is easy, take it for granted. Like this is a quadratic equation, right? X squared is equal to 1, right? But it can have more than 2 roots. If it is a prime p, then it has at most 2 roots, or exactly 2 roots when we are talking about a quadratic equation. But when this part is not a prime p, then things can be changed. Is that okay? So this needs to be a little bit careful. Okay, now let's talk about the other part. So we have shown that when m is equal to some prime p, then done. Okay? How about m is not equal to a prime? So that means what? That means m is equal to some number p times some number q, where p, q, they are greater than 1. So we have some p, which is greater than 1 and less than. So this p, you can think of it as a prime or any number that is less than m minus 1. Is that okay? Is that okay? So what happens in this case? Now, in this case, we are going to show that we will arrive at a contradiction. So it cannot be . So the second part is, so we are supposed that m is equal to some p times q, and m minus 1 factorial is equal to minus 1 modulo m. Okay? And our target is, after some steps, we hope to arrive at a contradiction. We hope to arrive at some contradiction. Okay? So let's see. So m minus 1 factorial is minus 1 is equal to minus 1 mod m. So what does that mean? So it means that m minus 1 factorial is equal to m times some number, let's say k minus 1. Am I correct? So this is the definition of modulo operation. Is that okay? Now, this side, m minus 1 is a multiple of p. P divides m minus 1 factorial. Yeah, because p is a number between 1 and m minus 1. So it appears inside this number. Is that okay? K, mk, p, this is also a multiple of p. Right? Because m is equal to pq. M has a p as a factor. So m times k is divisible by p. Is that okay? Good. Contradiction. This is a multiple. This is a multiple. Then this forces minus 1 to be a multiple of p, but it is impossible. Is that okay? Good. So a contradiction occurs. So we get Wilson's theorem proven. Okay. Good. That's it. Okay. Okay, so this part is done. Okay, next, let's talk about this Euler phi function. So this is a new topic. So we are going to define a function called phi of n. This counts. This is going to count the number of integers between one up to n such that their GCD with n is 1. So actually, how many numbers coprime with n? This is the value of phi n. So let's take a look at some example. So this is the definition. So let's take a look at some example. Let's say n and then phi n. So when n is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let's try these numbers. Okay, phi 1. Phi 1, what is phi 1? So look at the numbers from 1 to 1. How many numbers such that the numbers, let's say x, chosen from 1 to 1. Okay, how many cases are GCD x1 is equal to 1? 1. Okay, one case, so it is 1. Is that okay? 2. You look at the numbers from 1 to 2, and then ask how many of them has GCD equal to 1 with 2. So it is 1. There's one number, right? Okay. Actually, 3. Okay, let's look at 3. 3. Look at all the numbers from 1, 2, and 3. How many of them will be coprime with 3? 2 of them, right? 1 and 2 will be coprime with 3. So 2 of them. Actually, when we are looking at the prime number, let's say 5 is a prime number, then it is going to be p minus 1. 7 is a prime number, right? So it is going to be 6. Okay. Now, if you have 11 here, then it will be having a value of 10 here. Is that okay? Now, how about the others? So 4. So what is 4? So 4, you look at the numbers 1, 2, 3, 4, and then how many of them doesn't have any common factor with 4? So 4 is an even number, all even, right? So 2 to the power 2. So 1 and 3 will not have any common factor. So there are 2 of them. Is that okay? How about 6? 6, 1 and 5 only. Does that make sense? Because 2 not okay, 3 not okay, 4 not okay, 6 not okay, so there are 2 of them only. 8, 1, 3, 5, 7. These are the 4 numbers that is coprime with 8. 9. 9, you can have 1, you can have 2, you can have 4, you can have 5, you can have 7, and you can have 8. Oh, a lot. So there are six of them. Good, 6 of them. And then 10, how about 10? 10, okay, let me take a look. I guess it is going to be 4. Let's try. 1, 3, 7, and 9. These are the only numbers co-prime with 10. Is that okay? Okay, good. Now we are going to study this Euler-Phi function, and then it has a lot of interesting property. Okay, so we are going to have to see 2 interesting property. The first property is it is similar to, so we can define something similar to Fermat's little theorem. So what is Fermat's little theorem? Fermat's little theorem, if you still remember, it is like a to the power p minus 1 is equal to 1 mod p, right? When the GC of a and p is equal to 1, and so when we write a p, so usually we imply that p is a prime. So we are going to have this, we are going to look at this one. And then there is another property. This Euler-Phi function is a multiplicative function. What is meant by multiplicative function? So phi n, or phi, so phi pq is equal to phi p times phi q if the GCD of pq is equal to 1. So whenever a number can be chopped into 2 different parts, each part is coprime, then the phi pq is equal to phi p times phi q. So that's why I can calculate phi 10 quickly, because I checked. 10 is equal to 2 times 5, right? And 2 and 5 doesn't have any common factor. Okay, 2 times 5. So suddenly I look at this, 1 times 4, so I get a 4 here. Is that okay? So I can also talk about like how about phi of 40? So what is phi of 40? Phi of 40, how do I get? So phi of 40 is equal to, so from this table, okay, so I know that 40 is equal to 5 times 8. Okay, and then it turns out that 5 and 8 are coprime. Oh, so I can have 5 and 8, so I know that this is going to be equal to 16. Is that okay? Is that okay? And similarly, I can also get phi of, so I can also talk about what is phi of 105. 105. 105, it turns out that it is equal to 3 times 5 times 7, right? Okay, look at 3, look at 5, look at 7. Okay, so I know that it is going to be 3 times 5 times 7, so it is going to be 48. Okay? Because I'm applying this twice. 105 is equal to, let's say, 3 times 35. And then 35 is equal to 5 times 7. So I apply it a couple of times, so I can get this.